Directional derivative. So it's a directional derivative is what we used to come up with this idea that this is in fact the direction of greatest increase. So what that is saying is that, well, let's put it in context of a problem. Okay, let's talk about that hill or that mountain or the surface. Where we have our function z is equal to f of xy, and then we have a point AB up on the surface. And it turns out that from here, and we have to look at this in two views. One of them is a three-dimensional view. The other one is a two-dimensional view. The two-dimensional view is the xy plane. And so on the xy plane, what we're looking for is a two-dimensional direction that would tell us in our maps or in our compass which way to walk so that we feel the maximum increase in height, the steepest way to get up to the hill. All right, so it looks like if we do it that way, then we want to go maybe in this direction. So it looks like it's going towards the y-axis, maybe a little bit lower. So this here would be your gradient. More specifically, your gradient at the point AB. And if you look at that up on that hill, this is going to be the direction where you're going to go up the fastest. Okay? So does that picture make sense? If you can view this picture, then that's good. Also, so we say that the gradient of f at AB is a direction. This is a vector, right? And more specifically is a two-dimensional vector is the direction of maximum increase. Okay? What we didn't show last time is that if we go the other way, what do you think is going to happen there? If instead of going this way, we went the total exact opposite way of the gradient. So if you go the total exact opposite way of the gradient, you're going to be going in the maximum decrease. So the negative of the gradient is the direction of fastest decrease. Okay? All right, there's more information, which we can work out. But if you actually want to find So remember that these are directions. If you actually want to find the maximum increase, then the direction that you want to go towards is the gradient, right? So direction is the gradient. And usually we want to express this as a unit vector to get our directional derivative going. So the unit vector would be just the gradient divided by the magnitude of the gradient. Right? Is this too much symbols? A lot of confused looks out there. Okay, you got one thumbs up. I suppose I should keep moving. So the actual rate is going to be the directional derivative of your function in the direction of u, where u is going to be the direction of the gradient. And if you remember what that was equal to the gradient dotted with u. But u is equal to the gradient over the magnitude of the gradient. So this is the gradient dotted with the gradient divided by the magnitude of the gradient. And what is this equal to? Well, it turns out that when you dot something, a vector with itself, it's the magnitude squared. Did you know that? Like v dot v is equal to the magnitude of v squared. And then this is a scalar that we could just take out or leave underneath or do whatever. In any case, this is just going to be the magnitude of the gradient. So the direction of maximum increase is the gradient. The maximum increase itself is the magnitude of the gradient. Whoa. Yeah? No? Maybe? No? Well, maybe we could do an example and bring it down a little bit. Feel like you're hanging on in the building and then your fingers are starting to slip off. Or did you already fall? Right on the edge. Did you fall or did you jump off? I fell. All right, let's see if we can find one of those. So one of these, the 13, 14. So the question can be phrased a couple of different ways. Here's one way to do it. Find the maximum rate of change at f, the given point, and the direction in which it occurs. So because of this discussion on this previous page over here, we can just give the answers without thinking about it too much. and we kind of owe it to the properties of the gradient. So the maximum rate of change, without doing any work, and based on what we just said in the previous page, the maximum rate of change is the magnitude of the gradient. And then the direction vector is just the gradient itself. That's all, really, it boils down to. So if we work it out, let's actually do the problem. This is our f of x function, so we need, to fill our gradient, we need the partial derivatives. A partial of f with respect to x is going to give us our first component. So this is going to be 4, and then the derivative of sine is cosine, and then the derivative of the inside xy with respect to x, y is constant, it's just going to be y. And then the partial of f with respect to y should be pretty much the same thing. Okay, so if we put this in components, then we have the gradient in general. So if you were asked to give the gradient, then this would be your answer and you'd be done. Okay, but we're not done yet because we have a specific point to put it into. We want to evaluate it at this point. So your answer is not this. So this is one of the things that you have to be careful about. If you're being asked this problem in the context of a surface and a point, or a function and a point, and then you want to find the rate of change or maximum rate of change or direction or stuff like that at that point, then you have to make sure you put that point in. And I've been doing that, kind of taking it for granted, but now I kind of want to stress it since we're getting to do these actual problems. So what we really want to do is we really want to put the point 0 for x and 4 for y into this thing. So if 4 goes into y, this is 16, cosine of 0 is 1, and this x is equal to 0 will make everything else 0. So that's my direction vector. And then the magnitude of that, now that we have that, it's just going to be the length of that vector, which is the square root of 16 squared plus 0 squared, which is going to be 16. So your answers are scalar 16, the number that describes the rate of change, and the vector 16, comma 0, which describes the direction. Okay? That means if we go from here, at this surface, going through this point in any other direction, if we go to any other direction, then our rate of change or our derivative or directional derivative would be less than 16. Since this is the maximum, this is the largest maximum this is the largest directional derivative we can get. Okay? Is that clear? And like the idea of perpendicular stuff, we can extend this to higher dimensions. So this is a function going from R2 to R. We can go from R3 to R. Hell, we can even go to R5 to R. Any of those functions, we just keep building up these derivatives. Except the idea of directions for those really higher functions would be not something that we can visualize. Anyways, we haven't checked our answers. Since this is easy to put in, let's see what we can get. Where's the vector? Oh, there it goes. So the next problem we'll do is we'll do a problem where we're going from R3 to something else. Okay, it's not coming up, so let's just move on. Oops. All right, number 16 or 17 looks like it's one of those examples where it's a higher dimension. So let's take a look at those problems. Let's take a look at number 16. Give us a good practice on our derivatives. Same question, higher dimension. So essentially the same type of answer. And our answers will be, when they ask for the rate of change, maximum rate of change, you're going to put in your magnitude of the gradient. And then the actual direction is just the gradient. Except it will be in 3 dimensions. Your gradient is in 3D. So let's find the derivatives. Let's find f sub x, the derivative of f with respect to x. And y and z are constants, so I think there's just going to be a 9 plus 2y. Oh, that's just going to be 0. Wait, how are we going to do this? Yeah. So it'll just be 9 over z, I think. Is that right? Yeah, so you split the z up, it'll be 9 over z times x plus 2y over z, and then the derivative of 2y over z is constant, so that's going to be easy. Fy, kind of like the same thing, 2 over z, and fz. So this is our third component that we didn't have last time. Fz is going to be negative 1 over z squared. And then you got the 9x plus 2y is constant. I hope that's right. So think about the 9x plus 2y as constant. Leave that out in front. You have the 1 over z. So 9x plus 2y is constant. It'll stay there. The derivative of 1 over z is z to the negative 2 with a negative sign. So it's negative 1 over z squared. All right, now instead of writing the gradient vector itself for general x, y, z, let's actually put in the x, y, z. So let's evaluate each of these things at 6, 5, and negative 1. So here it's just negative 1 coming in. That gives a negative 9 for fy, evaluated at 6, 5, negative 1. Same thing. The negative 1 in for z, that's going to be 2 over negative 1. And then this one has all the components. Fz of 6, 5, negative 1 is going to be, now we've got to put the 6 in and put the 5 in. So 5 in there is 10. 54, 54 plus 10, 64. Over negative 1 squared is positive 1, but there's a negative sign outside, so it looks like this is going to be negative 64. Okay? So your gradient is going to be a gradient specifically at this point, so let's be clear about that. This is specifically at 6, 5, negative 1. Is going to be negative 9, negative 2, negative 64. So this is the direction of fastest increase. And then the magnitude of that is, well, the magnitude of this thing, big number. 81 plus 4 plus whatever 64 squared is. Do I know that? 64, what is it? 4096? So whatever that turns out to be. Maybe, yeah. 4171. Okay. So that's it. And then this thing didn't have any units, so feet per second or whatever. Rate of change is a derivative, so it's something per. It's the f value per measurement of the xy value. In this case, it's the f value divided by per the xyz, whatever that is. Meters usually. Okay. Is that clear now? The light appears. No. Whatever. All right, let's move on to yeah.
Professor, if they only give us 2 points, x and y, we need to plug those points into z?
Well, I don't think they would just give you just 2 values, 2 components, x and y, if your function has x, y, and z. So they should give you as many points as you have in how your function is defined. So if your function is defined as x, y, z, then you better have 3. And if they have 2 here, x, y, then you only have 2 here. At least that's how it should come up. Any other questions? What is it? 4,181? Okay, thank you. Yeah, I have a hard time adding, subtracting, multiplying. I was never really all that good at math. Anyways, let's put that behind us and move on. We have the idea that the decrease is basically the opposite of this, right? So let's take this very same problem, or let's take this very same problem. What am I going to do that? I'm going to copy this. And change the words here. So find the maximum decrease of f at a given point in the direction and the direction in which it occurs. So let's change this to a decrease instead of increase. And what we know is that if you're going to, instead of increase, you're going to decrease, we know that this is just going to be not exactly the gradient, but the negative of the gradient. It's the opposite direction of the gradient. Right? And I didn't tell you what the actual directional derivative was if you're going in the negative direction of the gradient, but can you figure it out? What is this direction of maximum decrease? Or what is the maximum decrease? So remember that the maximum increase, the actual rate of change, is the magnitude of the gradient. And so if you're going the opposite way, it's really the same slope, except you're going down instead of up. So this is a negative. Now we could do that with the formula. You can take your directional derivative formula and do the same thing with a negative sign. You'll see that negative sign will pop out, and that's exactly what's happening. So if this question got changed to this, we have the answers in the previous slide. This is just going to be the negative of the square root of 4181. And then this would be, instead of going in the same direction as that vector, I think it was -9, -4, -64. That would just be positive. 2, 4, 2. So it's the same thing, except we're going the opposite way. And that's it. Okay? All right, so that's the gradient being the maximum increase, the direction of maximum increase, and that's one important property for the gradient. The other important property for the gradient is the fact that it is perpendicular to a level set. Now, we talked about that. I don't know if we did an example, but let's dive into that now. And so I'm just going to copy that sentence that I had here. Gradient is perpendicular to its level set. And this is what we're going to talk about now. And what's important here that could be confusing, what's important here is that the gradient is the same dimension as your input vectors. Okay? So before we get started, let's just remind ourselves if your function goes from R2 to R, then your gradient has two components. Okay? And if your gradient, or if your function goes from R3 to R, then your gradient has three components. Okay? And this can grow to as high as you want this to be, so that your gradient for something like this is n-dimensional. Okay? So that's what you got to remember about the gradient. Because when you start playing around with this idea that it's perpendicular to a level set, that could get a little confusing. So it's the same dimension as your input. Okay? So now, let's think about this. If you had a function that looks like, let's say that looks like this. Let's just say you had a function that looks like that. Okay, what would you expect your gradient to be? Oh, let's give it a point. What do you expect your gradient to be? It's a two-dimensional vector, right? So let's take a look at this. Our gradient is fx is equal to, let's see, 2x minus 3y. Fy is equal to minus 3x plus 4y cubed, right? And so your gradient, and let's put 1, 2 in there. So it's going to be fx evaluated at 1, 2, and so 1 in for x, this is going to be 2. 2 in for y, this is going to be 6. 2 minus 6 is negative 4. Right? And 1 in for x is going to give us negative 3. 2 in for y will give us 8. 8 times 4 is 32. 32 minus 3 is 29. Right? So that's our gradient. This is a vector. This vector is perpendicular to something. Is this a vector that's perpendicular to our surface? No. Our surface is three-dimensional. This is a two-dimensional vector. What is this vector? It's perpendicular to what? A level set. Right? So let's picture this. Should we try to draw it? I mean, by that, I mean, should we have a visual of this? Let's have a visual of this. So I don't know if anybody took the time to actually figure out how the surface looks like, but this is a surface z is equal to x squared minus 3 times x times y plus y to the fourth. Let's see where that point is. Did you guys evaluate this at the point 1, 2? Oops. Lost it. 3x times y plus y to the fourth. And so the point that we are looking at, or we could be looking at, is the point 1, 2. And then if you put 1, 2 into the original function, you're going to get 11. There's that point. Did you see that point? Okay, but our vector isn't on the surface. Where is the vector? On the set. Where's the... Yeah. XY plane. Yeah, it's on the XY plane. So our level set is on the XY plane. So the question is, it's at 11, right? So what we might be interested in is taking a look at this function. Oops. Let's see if we can do some fancy double screening here. So the point 1, 2 is right here, right? So if I were to draw this vector would be from this point going in some direction. It's perpendicular to this point. So let's see if we can by the way, if you care to see what happens, this is actually, we're cutting it with a z is equal to 11 plane. So if we cut it with this plane, this is the image that we'll see, right? All right, let's take this and mark it up in our notes after I get this 1, 2 point in. Can I get it? No, no, no. I just got to take it out and just do it by hand. Gonna wait for the point to come around. Ready? Check. There you go. All right, so what do we have here? We have this point, 1, 2, in 2 dimensions. And then if you go from there and draw a vector 4, 29, so wait, what if you didn't know that? Nothing. So let's say from here, this is your point at 1, 2. And I just told you, or on top of the screen, or in the previous slide, it says that the gradient is perpendicular to a level set. Okay, this is a level set, a level curve to be more specific. And I know that my gradient is perpendicular to this level set. So if I draw an imaginary tangent vector, I would have my gradient that's perpendicular to this. But remember, last time we had this issue where we had 2 possible gradients to choose from, right? So the question is, which one is the correct gradient to choose? So what do you guys think? Yeah, so this vector going up is one possibility for the gradient. The vector going down here is another possibility for the gradient. So which one do we choose? How do we know which is which? One's going in the direction of maximum increase, and one's going in the direction of the maximum decrease. So what you have to do is that you can't, if you just had this picture here on the right side, you're not going to be able to answer that question. What you need is a picture on the left side to actually see what's happening on the surface. Or you probably need more level curves and labels on them which way to go. So it depends on if you step in a particular direction, if z is going to be negative or positive. So you're here. Now this is hard to see. I thought it was a good picture too. You're here. Which direction would you go to the fastest increase? Can't tell. All right. What if I do this? If I have another level curve. So this is the level curve that we have drawn here is a level curve at 11. Z is equal to 11. And if I go one higher, it looks like my curves are going to go outward, right? So this is a level curve, Z is equal to 12. And I can go more and more level curves if I want to. Okay? So now given that idea, which of these 2 vectors is the gradient vector? The up one, this one going up. Because it's going towards a Z level of 11 to a Z level of 12. It goes higher. Right? So this is not the curve that we want. This is the curve, this is the vector that we want. So this is your vector, gradient vector. perpendicular to a level curve going in a direction of maximum increase. Does that make sense? The opposite way is going down. So what was it again? I covered it up here. -4, 20, 29. So -429, and does this look like it might be -429? It's negative in the x. That makes sense. It's positive in the y. So yeah, so it looks like it's right. Okay? So that is, in fact, your level curve. And your gradient is perpendicular to a level curve. All right? This totally didn't answer any quiz questions, just in case you're looking. You're not looking? Okay, so perpendicular to a level set. And our function here was a function from R2 to R. So we can extend this idea to have a function from R3 to R. So now, let's let f be some function from R3 to R. And let's make one up. So f of x, y, z equals to something nice and easy. You got x squared plus y squared minus z squared is equal to, well, just leave it like that. Okay, so x squared plus y squared minus z squared. So what do we want to say? We want to say that note the level sets are surfaces. Okay? Remember, if you take a look at this function, we can actually write this function as w is equal to f of x, y, z, or w is equal to x squared plus y squared minus z squared. If we include that w, we're looking at a fourth dimension and trying to visualize this, and you can't unless you go to Santa Cruz. But besides the point. So what we want to do is we want to take a look at what if w was equal to a constant. And so if w was equal to a constant, then we're looking at level sets. And more specifically, if w is equal to a constant in this particular scenario, we have now a relationship between x, y, and z, and that gives us a surface. Okay? So if we let w equal to 0, we're going to get a surface. If we let w equal to 1, we're going to get another surface. If you let w equal to -1, we're going to get another surface. Those are all going to be level sets for this four-dimensional function. Or if I rephrase it, those are going to be level surfaces for these four-dimensional functions. Pick a number. Pick a small number. So 4, 7. 7's fine. Let's do 7. So if we consider the level set 7, we got x squared plus y squared minus z squared is equal to 7. Now, if we spend a little bit more time on this, I would just ask you what this is, and you should be able to tell me. What is it? Close? No? No? Hyperboloid. It's a hyperboloid. One sheet. This is a hyperboloid of one sheet. Okay? If it was 0, you would have had cones. If it was negative, you would have a hyperboloid of 2 sheets. All right, so let's just for now think about this as a hyperbola to one sheet. Well, let's just think about it as a surface. Doesn't really matter. So this is a surface. So if I give you a point, so I think Rick asked about a point here. If I were to give you a point here, I need to give you a point with 3 components in this. If I just give you a 2-dimensional point, this isn't going to work. So let me give you a point. Let P equal to, I don't know, an easy one would just be 0, 0 something, right? 1, 1, 2 would work. So 1, 1, 2. No, it doesn't equal. I need something that equals a 7. 1, 1 square root of 5. Will that work? Just change W. What do? Root 700. Would that work? Yeah? All right. Thanks. So we have now a point on the surface. According to, I was going to say according to legend, according to what they said, if we take the gradient of this, we're going to get something that's perpendicular to this level curve at this point. We're going to get a vector perpendicular. So the gradient is equal to, can we take the gradient quickly? It's 2x, 2y, minus 2z. And then if we want to evaluate this specifically at this point, root 700, we're going to get, well, 2 root 7 and 0 and 0. So that means this is going to be a vector perpendicular to that surface at that point. And just to get, and see if we can do this quickly, we're 2 minutes past, but let's do it. So our surface is x squared plus y squared minus z squared equals 7. And then our vector is a 3-dimensional vector. What's our point? 0. Root 7. 0, 0. I want this for now, and then the gradient.
It's 2 root 7, 0, 0, 0.
Oh, you can hardly see it, but let's see. So it's this arrow, this red arrow coming out of there, and that is in fact perpendicular to the level surface. Okay? All right, so there's a couple more things I want to say about this, and so next time we'll pick up on this and then talk about max and mins. Have a good weekend.